Hello, I'm Dr. Kathleen Schmidt from Lawrence Livermore National Laboratory. Welcome to the Data Science Institute's virtual seminar series. With Lawrence Livermore being home to many challenging data sets, as well as some of the world's most advanced supercomputers, data science has become an essential discipline in the lab's key program areas. The DSI acts as a central hub for the lab's data science activities by fostering collaborations, promoting research, and engaging in outreach activities. Our DSI staff work in a variety of areas, including artificial intelligence, big data analytics, computer vision, machine learning, predictive modeling, statistical inference, and uncertainty quantification. The DSI hosts events like this seminar series to introduce new ideas and potential collaborators to the lab. We invite speakers from other institutions, both from the Bay Area and beyond, to share their innovative projects, approaches, and ideas with our data science community. We're pleased now to include a wider audience beyond the lab to engage with us through this series. You can read about past speakers on our website, data-science.llnl.gov, or email us at datascience@llnl.gov. Thank you, and enjoy the seminar.
So welcome to the DSI seminar series. I'm Katie Schmidt from the Applied Statistics Group at Lawrence Livermore, and also the DSI seminar series coordinator. And remember, for those of you coming in from the lab, this is an external event, so tailor your questions accordingly. And if you do have questions, please put them in the Q&A bar at the bottom. You won't be able to unmute, so we'll make sure to hit up your questions at the very end. So I'm pleased to present our speaker today, Bobby Gramercy. He's a professor of statistics at Virginia Tech, and he has a great relationship with the lab, currently a VSP with the Applied Statistics Group, and his research interests include Bayesian modeling methodology, nonparametric regression, sequential design, and UQ. Today he'll be discussing the importance of replications when doing experiments.
Thanks so much, Katie. I'm going to try to share my screen. So I think you can see my slides now. I'm sure you'll let me know if you can't. Thanks so much for having me here today and for the nice introduction. Man, I had a great time visiting you guys in the summer 3 years ago, and I sure thought I would be out there again sometime soon afterwards, but then COVID happened. But I hope we can make it work again. I think just so many great problems at the labs and at Livermore in particular, and cool people to work with, so I hope we can sort of strike up some collaborations at some time in the future. I'm going to tell you about work today on surrogate modeling for stochastic simulation experiments. This is work primarily by a postdoc of mine from several years back, Mikhail Benoit, who is now at INRIA, and a few other collaborators along the way. Okay, so like I said, this talk is about surrogate modeling, or about meta-modeling of computer simulation experiments. So let me set that up for you, and then give you a little bit of review of Gaussian processes, which are the main surrogate model or meta-model used in this context. So I'm going to be working with a computer simulation experiment that I'm just going to call F. So F takes some input configuration parameters X and returns a real valued output Y. And getting that output Y requires a big computer simulation. So think supercomputer evaluation of maybe a coupled system of differential equations or something like that. So the idea is that there's maybe a mathematical model and a computer program that solves that mathematical model, and that computer program is our function F. And because it takes a lot of time or computing resources to evaluate F, it makes sense to design an experiment and then fit a model so that you can understand the outcome of that experiment and use it to make some decisions or some visualization or something. So for that, we do what's called emulation or surrogate modeling, but really that's just regression. So I want to fit a regression to a designed experiment. I choose some X's and Y's, N of them, capital N of them here, that I'm going to run my simulator F at, and using that data, I'm going to fit a flexible model so that I can make predictions in novel circumstances, or maybe produce visuals, or do a sensitivity analysis, or optimize some aspect of the system. I could fit a linear regression, but that would probably be too crude. I could fit splines. I could fit deep neural networks. But the model that has percolated to the top of the hierarchy for surrogate modeling or emulation, the regression model, is based on multivariate normals, and it's called Gaussian processes. So the idea of a Gaussian process is to model your responses y. This is a vector of n y values as a function of pairwise distances in the input space through a Gaussian distribution. Now I'm going to give you a lot more detail on that. So I'm going to skip ahead now and tell you why, and then I'll show you how. So why is this the model that people like? Because the predictions are accurate, especially when dynamics in the input-output space are relatively smooth, as they are for many physical relationships, and they have appropriate coverage. That means predictions and error bars out of sample are appropriate, and because they can interpolate. Historically, these computer simulations were deterministic, so there was no noise in the system, and interpolating is what you'd want them to do. I'm going to talk to you about situations where we don't want to interpolate, but it makes sense to start there. So let me give you some more detail on how Gaussian processes work. I like to do this in my talks to give at least 15 minutes of classroom-oriented presentation so that I can teach somebody something new maybe, but also so that people who are familiar can get a sense for how I think about problems and get a better feel for the notation and so on that I'll be using for the rest of the talk. So let me review Gaussian processes for you. When you hear people talk about Gaussian processes, they take a Bayesian perspective. They talk about priors over functions and posteriors over functions. You don't need to be a Bayesian statistician to appreciate what's going on, though, although I will use some of that terminology. Let me just show you how to generate random functions following a Gaussian process. You could call that the prior if you want, but just think about generating random functions. So I'm going to take some inputs. That's not going to be the random part. The random part is going to be the output. So let me take some inputs in my input space, and then I'm going to build a covariance matrix from distances between pairs of those inputs. So here I'm exponentiating minus Euclidean distance. So this is going to give me stronger correlation between the y values the closer the x values are together. And the farther apart they are, the lower the correlation. And take that covariance matrix and put it into my favorite multivariate normal random number generator. So that's the algorithm, 3 steps. In R code below that is my implementation of that algorithm. This is an R markdown talk, so what you see is what you get. The code is actually evaluated and used to produce the output and the figures that are printed on the screen. I won't go line by line through the code, although I might point out some lines from time to time. For example, my covariance matrix is e to the minus distance. I've had to add a tiny bit to the diagonal to keep the matrix numerically positive semi-definite. And then I put it into my favorite random multivariate normal generator. In fact, I'm generating 3 realizations, so I can plot 3 different random functions for you on the next slide. Okay, so here are those 3 random functions. So this is how you use a Gaussian distribution, a multivariate Gaussian distribution, to generate random y's as a function of x through a covariance structure that decays exponentially fast as a function of pairwise distance in the input space. All right, so generating random functions is fun, but it's not what we really want to do. What we want to do is we want to solve an inverse problem. Given some examples of a function, a data set of x's and y's, we want to know what functions could explain those values. So what random functions could explain those values. So we want to know about the conditional distribution of y of x given the data D. So if what I just showed you is the prior, then after I condition on data, I must have what you could call the posterior. Again, I don't want this to be a talk in Bayesian stats. We can call this the predictive distribution if you want instead. I'm fine with that too. All right, so how are we going to derive that predictive distribution? Well, actually, it's just a Wikipedia result. So everything to do with Gaussian processes is summed up by this slide, which was plagiarized from that Wikipedia page. So what does that Wikipedia page say if you clicked on that link? I'm not going to click on it. It says that if you partition a multivariate normal random vector into 2 components, here the components are x1 and x2, and similarly partition the mean vector and covariance matrix into 2 and 4 pieces respectively, then you can derive the conditional distribution of one component of the partition given the other. So here I'm looking at the distribution for x1 given x2. Like many things Gaussian, it will also be Gaussian. Marginals of multivariate normals are Gaussians, and conditionals of multivariate normals are Gaussians. So this particular conditional has this mean vector and this covariance matrix. The mean vector is kind of like a linear projection. It almost looks like a regression in and of itself. And the covariance matrix is a kind of quadratic form that is a reduction from the marginal variance. So if the marginal variance of x1 is here, because that's the 1-1 component of the covariance matrix, the conditional covariance is reduced based on the distances between the two sets of points. Or not, I say distances because I'm going to apply it in a moment in the Gaussian process context. So I'm just going to take that Wikipedia result and I'm going to use it with my covariance structure. Okay, so here I've just done that kind of generically. I'm going to have a mean vector that's some kind of regression, so it's a linear projection of the y values, and a covariance structure that's reduced by an amount that has to do with the distance between the training and testing locations. So just to kind of go through some notation here, squiggly x is my testing set. The y's are my training y's. The x's here are my training x's. So the mean of this is like a linear projection, but in distance space or inverse distance space. And the variance is a quadratic reduction in variance based on distance to nearby training locations. These are sometimes called the kriging equations in spatial statistics. You can say all sorts of things about them. For example, they describe the best linear unbiased predictor under some technical regularity conditions. But for us, they're just a conditional distribution that you derive from a multivariate normal, where the covariance structure is a function of distance. And you may have noticed that I don't have anything for the mean. The mean is 0 throughout, except when we condition, it's not 0, of course. It has to do with the y value. All of the action of this is in the covariance structure, which is kind of an interesting thing about the setup. All right, let me illustrate that for you in a real example. So suppose I have a function f, which for us is going to be the sinusoid. So this is my expensive computer simulation. I'll put expensive in quotes, that I'm going to Spartanly evaluate at 8 evenly spaced inputs in one period of the oscillation of the sinusoid. And I'll calculate pairwise distances and I'll exponentiate them. And then I'll do a similar thing for the testing set. So I'm going to make a grid. These are my calligraphic x's, which I call xx in code. So I'm making a denser grid in the input space, and I'm calculating pairwise distances between those locations and exponentiating them. And then I'm getting the between training and testing distances and exponentiating those. And now I have all of the quantities that would be involved in the big covariance matrix of training and testing observations, and I can apply the conditioning to get the distribution of the testing given the training. So I will do that regression. So this is the linear projection in distance space and the quadratic reduction in covariance after conditioning. Now I have a mean vector and covariance matrix that I can plop into my favorite multivariate normal random number generator. And here I'm going to collect 100 realizations from that Gaussian distribution. And I'll also extract some quantiles down below so I can make error bars for you. And this is a plot of the training data and the predictive distribution. Each gray line in this plot is one of those 100 random realizations from a multivariate normal. And you can see that they all interpolate the data. So each gray line goes through the black dot. The black dots are the training data. The mean of all of those gray lines is in black. You can probably see it most clearly here. Next to it is the blue line, which is the truth. And you can see for most of the input space, the truth and the mean line are very close. They overlap one another for most of it. And the red dashed lines are a pointwise measurement of uncertainty. They're quantiles, 95% quantiles. And people like to talk about the football shape of those quantiles or the sausage shape of those quantiles. I think that depends on whether you're European or North American. North Americans like football because footballs look like that, and Europeans think footballs are rounder, so they call this a sausage. You can see why people would like this for deterministic computer model evaluations where there's a degree of smoothness because it interpolates, because the uncertainty quantification is sensible and the predictions are highly accurate. Okay, lots of ways that you could embellish this. What I showed you is the basics, but you can do whatever you want in this context. You can define covariance in many different ways. Distance is often the feature. Here I'm using distance, but I'm doing it coordinate-wise, and I've introduced a parameter theta. Sometimes people call these hyperparameters because the real learning happens in the multivariate normal conditioning, not in the tuning parameters. So hyperparameter theta, this is called a length scale that allows the rate of decay of correlation to be different in different input directions. And I've also got a parameter tau squared here that's called the nugget. This is introducing a white noise parameter into the process so that I can get noisy data, so I can smooth noisy data. And the new here is called a scale parameter. This allows me to model functions whose amplitude is bigger than 2, because a Gaussian would have an implicit scale of 1, which means that most realizations, 95% of them would be between -2 and 2. So this allows that to generalize. So I've introduced 1, 2, and then a vector 3 parameters here. And how would you learn those? Well, you would learn those the same way you would any other parameter in stat. So many choices, right? You could do cross-validation, you could do method of moments, you could do the eyeball norm. I like the likelihood because it's pretty automatic, and this is a Gaussian, so the likelihood is available to me through a lookup on Wikipedia, and I can take its logarithm and I can differentiate it with respect to the unknown parameters. So here I've differentiated the log likelihood with respect to the scale parameter nu, set it equal to 0 and solve. I can do that in closed form. So I can get the amplitude without doing anything fancy statistically. I can differentiate with respect to the other parameters. I'll need to do a little more work to do that, to use matrix chain rules, but it's still available in closed form. Solving, setting that equal to 0 and solving is not available in closed form, but numerical methods work really well, like Newton-like schemes work really well for that. So I'm going to code that up for you. Here's a whole slide of code. This is the only slide like this in the talk, but this is just me coding up the negative log likelihood and the negative gradient of the log likelihood. So in total, maybe 20 lines of code, and I can pop that in, so as an objective and its derivative, into my favorite optimizer and solve. And that's what I'm going to do on this slide. So ultimately on this slide, I'm going to use optim in R with a negative log likelihood and a gradient, and learn hyperparameters, and then I can make predictions. I'm going to do this on a different problem. So we looked in one dimension at that sign you saw before. Here I'm going to do a two-dimensional problem where the response surface is clearly nonlinear and also observed with noise. So when I put those XY values in, I get estimates for hyperparameters. So this is a theta 1, and this is a theta 2, and this is a nugget. That's tau squared. Those parameters aren't very interesting to look at, the values anyway. They don't mean anything special. What's important is how they work with the covariance structure in the conditioning involved in prediction. So I'll just take those numbers and put them into my covariance matrix, and then do the regression, do the multivariate normal conditioning. So that's happening in these two lines here. So everything that comes before that is just building the covariance matrices with the parameters that I've learned, and then applying multivariate normal conditioning. And then I can make predictions. I can look at the mean surface and the standard deviation surface. So mean surface on the left, standard deviation surface on the right. And you can see that it has features in common with the sine example, although a little bit harder to see because the dimension has increased. I've got a nonlinear function. This is my mean, very nonlinear. And in terms of uncertainty, my uncertainty is lower in red near the training data sites, which are the open circles, and higher in yellow away from it. So it's got that sausage or football shape in 2 dimensions now instead of in 1. All right, so that's my Gaussian process review. Of course, there's more to it than that, but that's the essence of it for the purposes of this talk. So what is this talk about? Well, this talk is about bigger computer experiments when there's noise. So my setup here is that Gaussian processes are popular in geostats, in machine learning, in computer simulation experiments, and people are pushing the envelope in those contexts. In computer experiments, there's lots of stochastic simulations going on now in epidemiology, in inventory management, in physics. And those stochastic simulators sometimes have very low signal, so they have high noise, low signal, and they often have noise level that's changing over the input space. So I want to address those 2 things: low signal, high noise, and noise that's changing over the input space. And I'm going to do those one at a time. I'll take the first one first and the second one second. As a kind of setup here, though, if you have noise, then you probably need more data to isolate the signal compared to if you don't, or compared to if you have very little noise. That's sort of like a basic statistics fact, right? The more noise, the more data you need to isolate the signal. But the trouble with Gaussian processes, for all the amazing things they do, they don't work well when the training data size gets big, because I need to work with multivariate normal distributions, and that involves matrix decomposition. To evaluate the likelihood, I'll have to invert a covariance matrix, and I'll need to take its determinant. And then to predict, I'll also need to take the inverse of that matrix. The best way to do that in general is with a Cholesky decomposition, and that has a cubic cost. And that's going to severely limit the training data sizes that we can work with Gaussian processes. For a modern desktop machine, you can work with a few thousand training data locations in a reasonable amount of time. By reasonable, I mean tens of minutes. So what can be done? Well, the first trick I want to show you is the oldest trick in the book. Replicate. You have to separate signal from noise, and a great way to do that is with replication. So by replication, I mean to take many observations y at the same input x. That's a replicate, when you take many y's at the same x. That's a statistically efficient way to separate signal from noise, and it turns out that it's also a computationally efficient way with Gaussian processes. Okay, so I only have one slide on this. There's more to it than I'm showing you. But when you replicate, you get a pure look at variance. So you're not confused about whether you're seeing signal or noise. You're seeing noise. So that's what makes it statistically efficient. You know what you're getting. It's computationally efficient because you can show that there are fewer sufficient statistics under a replication regime. So here's some notation. If I have a potentially large simulation campaign, capital N, but I've only run it at little n unique inputs, so I've got lots of replicates, then something called the Woodbury matrix identity allows you to show that the sufficient statistics scale with the unique inputs rather than the full set of simulations. In particular, you can get a mean prediction and its variance by working only with little n quantities. So I've got matrices here that only involve little n, not big N things. And if you think about how to do this, this just involves replacing the original data with its averages across replicates. There's a little bit more to it than that, but that's the basic idea. That idea, I think, originates in the sort of informs community, the operations research community from 2010, but they didn't recognize that it was an identical result. They had a limiting result with expectations, but this is actually a one-to-one identity. You can do the same thing with the log likelihood. So you can show that you only need to manipulate order little n quantities in order to work with the likelihood and its derivatives, which means you could put it into a numerical optimizer and it'll be a lot faster when there's a high degree of replication. So there's a lot of formulas on this slide just to show you that it's available in closed form, not formulas I really want to go through. Let me show you it in action. So I'm going to revisit our 2D problem from earlier, but it's going to be a much bigger version of it. So before, I think I had 20 training data locations. Now I have 100 unique training data locations, but a random amount of replication so that I get about 2,500 total simulations. The code down below is implementing that. It's a little bit more code than the 2 bullets that describe the data generating. So I've got a training data set with about 2,500 runs, but only at 100 unique input locations. I'm going to introduce some software here. So we have a package called HetGP on CRAN. You'll see why it's called HetGP in a minute. So let me delay that for the time being. This is the right way to use the code in the package to perform the inference. So you give it the X's and Y's, and you give it some parameters that control the optimization. And under the hood, it does exactly the same thing that I showed you a few slides back. It sets up a likelihood and its gradient and sticks those into the optim command, and out come the hyperparameters. And when you do that with this run of the code, this is the output you get. So these are the estimates of some of the parameters. It doesn't matter what their values are. And this is how long it takes. So it takes 5/100ths of a second. So that's instantaneous, right? 2,500 training data locations and a result in less than a second. The software kind of lets you cripple it if you really want to. This is the wrong way to run it, and I don't know how you would guess that this was the wrong way. It's not meant to be intuitive to use it the wrong way. But if you give it the information in this way, it won't recognize that there are replicates, and it'll still run, and it'll give you about the same estimates of the hyperparameters, but it takes a lot longer. So this is the ordinary Gaussian process way, which I'm not good at that math in my head. Let's say thousands of times slower. So although both methods are using cubic matrix decompositions, the n involved in those cubic computations is very different. One of them is only 100, and the other is 2,500. So that's a huge difference in work, even though the computational order is cubic in both cases. So replication is a great way to separate signal from noise and not take a computational hit when working with Gaussian processes. So now I'm going to pivot to input-dependent noise, which is a more interesting subject, because Gaussian processes are not so good when the noise is changing in the input space. This is my favorite demonstration of that. This is called the motorcycle accident data. It's actually a computer simulation experiment. So it's simulating the acceleration experienced by the helmet of a motorcycle rider just before, in the low times here, and then after an impact. So you can see that you can guess where the impact here is at about time 15 or something like that. There's low noise in this pre-impact regime, and there's also low signal. And then there's big signal, big noise, and then it kind of calms down again. Both things kind of level out, both noise and signal. So this kind of behavior is not well modeled by Gaussian processes because the default setup only uses pairwise distances to describe correlation. It's not input dependent. It's only displacement dependent. So it's unable to get the regimes that are going on here in terms of the variance. So this is a form of non-stationarity in Gaussian process, or non-stationarity in data generation, that's not accommodated by this Gaussian process. In particular, it doesn't get the variance non-stationarity, or what you could call heteroscedasticity, which is the word for input-dependent variance that I think comes from Greek. All right, so how do you deal with that? There are lots of ideas for how to handle this with Gaussian processes because it's an important class of problems. There's only one setup that I think works really well, and it's actually one of the oldest. It comes from a NIPS paper in 1998. But the disadvantage to what they present in that paper is that they use MCMC. And the MCMC is just too much work, I think, except if you have a small data set. So I guess they were a slave to the times. In the late 90s, MCMC was popular, and that's what they developed. But otherwise, it's a good idea. So let me describe their idea to you. And their idea is very simple. It says, do what you did for the mean with the variance too. What did I just say? So we put the y values under a multivariate normal prior with a distance-based correlation structure. That's what a Gaussian process is. So that's what I mean by do for the mean. That's what we did for the mean. Do that for the variance. Put the variances, so call delta the variances. You don't know what they are. They're latent variables. You don't get observations with them, but you can notate what they are and give those a multivariate normal prior with a distance-based correlation structure. The notation here is messy because I've got to invent new letters for the same thing that I had before. And then I can smooth those by doing a linear projection in distance space. So I can enforce smoothness in variance the same way a Gaussian process enforces smoothness in the mean. But now I have parameters to learn because I don't know what these values are, so I've created unknowns. And I need to learn those unknowns. And that's what they used MCMC for in that paper. So I'm going to appropriate this idea. And I'm not going to do MCMC. I'm going to do one other thing differently. And that one other thing is I'm going to be careful to introduce latent variances only for the unique input locations, not for every replicate, because that could end up being a computational nightmare if I have lots of replicates. So I'm going to have a latent noise variable for each unique input, and I'm not going to do MCMC. Instead, what I'm going to do is likelihood-based inference, just maximize. So I'm going to calculate the likelihood, and I'm going to calculate its derivative with respect to all unknowns, which is tractable analytically. You can get a closed form expression for both things. And although it's now a high dimensional optimization, the surface that you're optimizing over is very well behaved. It's not convex, but it's no less convex than any of the other Gaussian process things that people work with involving the likelihood. So this works exceedingly well. You could stick this in as an objective and its derivative into your favorite optimization software, and it will come back with estimates for all of the unknowns in relatively few evaluations. So I'm going to show that to you. I'm not going to code up every little bit. We're going to use the library, but the principle behind it is the same. I'm putting something into the optim function in R, but that something is a little bit more complicated than before. So I'm going to give the X's and Y's from the motorcycle problem to the flagship function of our het GP package, so heteroscedastic Gaussian process, maximum likelihood estimation, fast. There's actually a degree of replication in this data. It's not high, but there are some replicates, and it takes less than a second to learn more than 100 latent variance values, and then the other hyperparameters that are involved in the Gaussian process. And then I can use the built-in predict method to get predictions, and I can extract quantiles, and I can show those to you on the next slide. So here's the motorcycle data and my predictions and error bars. You can see that the quantiles are narrow to start with, and then they're wider, and then they're a little narrower again. On the right panel, I'm showing you this latent variance process. So the black line is my prediction for variance, which starts out low and then goes up, and then plateaus and then goes back up again and then comes back down. You can see it's a nice smooth function. In fact, what we've done is we've modeled the logarithm of the variance as a Gaussian process and then exponentiated to make everything look positive. It's supposed to be positive, otherwise it's not a valid multivariate normal. The green dots here are moment-based estimates of variance that come from the replicates in the data, so that you can get a sense for how that's being smoothed, right? So I have some low variance replicates and some high variance replicates, and this is smoothing those values. And it's getting more information from the inputs that don't have any replicates, which aren't shown on the plot. All right, that was kind of, it says real examples. That was a real data set, but it's kind of an old and toy one. Let's go to a couple more ambitious examples. So one application area that I like this for is epidemiology, which is a hot subject at the moment. I'm not going to show you anything COVID related, but I have used this setup with Ebola data. This setup here is just a simple susceptible, infected, recovered model, and it's not for any of those two applications, but it's rich enough to show you what's going on and show you what the benefits are. So here I have an initial state, so these are my inputs, the initial number of susceptible and infected individuals in a population, and then stochastic continuous time Markov dynamics allow the system to evolve through expectations over a period of time. And then at the end, what we look at is the number of infected individuals after the simulation is finished. And what you get is a nonlinear surface and a surface where the noise is changing in the input space. And I can show that to you by doing a simulation campaign. So here I'm going to set up a simulation campaign in this two-dimensional input space that's very similar to the one we did in our earlier example. There are going to be 200 unique input sites and a random degree of replication over those sites, sometimes very high degree of replication, so that the total design size is about 10,000. In this case, it's a little bit smaller, considering how the random number of replicates worked out. And I can take those X values and stick them into our simulator. So our package comes with this function SIR eval, so you can reproduce this experimental setup if you want to. I take those X's and Y's and put them into my MLE function, and it takes about 4 seconds to learn all 200 latent variables and all the hyperparameters that go along with it. It's not too bad for 10,000 training data sites with a Gaussian process, I think. And then I can make a prediction over the input space and show you what that looks like on the next slide. So the mean surface is relatively tame. It's not linear, although it looks so. It's got kind of a exponential growth going here from small infected susceptible to large infected susceptible. This makes sense. The more infective and susceptible individuals, the more infected people you'll have at the end. But the variance is kind of surprising, or in this case, the standard deviation. It says you're most uncertain when you have a large susceptible population and a moderate number of infected individuals, because that's when the randomness really takes hold. You could get lucky and the infection will die out quickly, or you could get unlucky and the infection will exponentiate and explode quickly. And you don't know in that regime. That's where your uncertainty is highest. So this is a problem where the variance is more interesting than the mean. So modeling with a flexible non-parametric function structure provided by Gaussian processes is important in this example, especially for the variance. Here's another example. This comes from Radu Herbe and Mark Berliner at Ohio State. So they developed a simulator that models the concentration of a tracer within a spatial domain. And in this application of that model, we're going to look at oxygen concentration in the ocean, so over latitude and longitude. You can get the source for this from their GitHub page. I've worked on a little bit of an R wrapper that makes it easy to put that into this R Markdown presentation. So there are 4 inputs to their simulator, 2 spatial coordinates and 2 diffusion coefficients. If you imagine what you might do with this simulator, you might want to solve an inverse problem. You might want to do some field measurements in the ocean of oxygen concentration, and then try to invert the diffusion coefficients using that data. I'm not going to try to make plots in 4 dimensions. I'm going to stick to 2. So I'll focus on the spatial coordinates, but I've got some examples where we do the whole thing in 4 dimensions if you'd like to see it. Here I'm just going to convince you that it's nonlinear and heteroscedastic. So I did a limited simulation campaign for just one of the inputs. This is along the longitudinal slice with the diffusion coefficients held fixed. And you can see that it's nonlinear. It's low, then it's high, then it's low, then it's high. And it's heteroscedastic. It's got low variance, high variance, and then low variance again. So a heteroscedastic Gaussian process would be a great fit for this data. Here I'm just going to do something very simple. I'm going to pick 25 space filling inputs and 20 replicates at each one. So a pretty big training data set. And then I'm going to apply our Latent GP idea. This is not a good design for this experiment. deliberate in that because I'm going to transition next to showing you how to make a good design for this experiment. But for now, let's just see what it looks like. You can see that the mean surface is nonlinear. There's a high region, there's a low region, there's a medium region. Each one of these 20s is giving you the location of a training data site and indicating that 20 replicates were generated there. The standard deviation surface is nonlinear. It's got a high standard deviation area and a low standard deviation area, and some in-between spots. Okay, one last example before I transition to design. This is an 8-dimensional problem, and I'm not going to describe it too much or its output. It's really hard to talk about experiments of this size with this input dimension and all the other things that we tried. But this is a great example from business on inventory management. It's got 8 items that you're trying to keep in your inventory to make sure you can fill random demand. We did big experiments with 5,000 points, but it was computationally reasonable. And we compared ourselves to a lot of other methods and found that ours were the best. So ours are the ones in red here. Higher is better because we're looking at a proper scoring rule. And I want to just kind of extract out one of those to make a comparison to it later. So there are 1,000 unique inputs, 5,000 odd total, so almost degree 5 replication. And one of our scores was this number right here. So what does that number mean? Nothing, but I'm going to compare to it later with a better statistical design. So I'm going to transition now into how to design an experiment for this kind of stochastic computer model simulation. And this is the last topic before we wrap up. So on this slide, I'm saying that almost anything you could think to do at the beginning to design an experiment like this is not going to work out well. You know, there's just too many unknowns. You might have the instinct that you need more replicates in the high noise region. So you might want to design your experiment to have more replicates there, but you might not know where that is. And how can you discover where that is unless you do a smaller experiment first? So I think the only thing that makes sense in this context is to build up your experiment in batches or one at a time. I'm showing you one at a time here. Those of you who worked with Boya, who was my PhD student at Virginia Tech, we did a batch version of this basic idea. So here's the setup. Start with a small experiment and then fit a Gaussian process or a heteroscedastic Gaussian process and use that fit to solve a decision problem about what new input to try next, and then repeat. Here we're trying to create a virtuous cycle between learning and acquisition. Right? Model fit influences model or data choice, which influences model fit. And if you do that right, you create a feedback loop that reinforces learning. Lots of ways you could do that. Maybe you're familiar with Bayesian optimization. So that's acquiring new data in order to find the minimum in the input space. Here, what I'm going to show you is maybe more difficult conceptually, but more common, I think, as a design goal. I'm going to try to design to minimize my uncertainty in predictions everywhere. And one way to do that is by looking at predictive variance as a function of the inputs and integrating overall inputs. So I want to make my predictive variance everywhere in the input space as small as possible. Here I'm notating that variance in terms of n+1 design locations because I want to use it to choose the n+1 one. And it turns out that that future variance is available in closed form, and so is its integral. And we were not the first to do this integral in closed form, but we were the first to do it for heteroscedastic Gaussian processes and with the Woodbury trick to make sure that it used only order little n sufficient statistics. And some of the math for that is here on the slide, but I'm not going to go through it. You can also take the derivative of this integral in closed form and evaluate it in time to do with only little n things instead of big N. So you can put the acquisition function for sequential design into your favorite optimizer and solve for the coordinates of the new location according to that criteria. Before I do that, I want to take a little sidebar here and show you what's happening when you use integrated mean square prediction error to drive sequential design. So here, what am I showing you? I'm showing you two variance functions. You could call them noise functions R. So that's what's on the y-axis. So I've got a green noise function and a blue noise function, summarizing my uncertainty in outputs as a function of inputs. So one-dimensional input, noise on the output. The red dots are supposed to indicate information that's already been acquired. So at 5 of the inputs, I know what the variance is. That maybe isn't realistic in practice, but just suppose that at 5 locations I know where it is, so my hypotheses agree, but everywhere else in the input space I don't know. I'll have to acquire data in order to figure out what the noise is. But in the meantime, I'm going to use what I believe about the noise surface in order to make that decision. And I'm going to make that decision with integrated mean squared prediction error. So I'm coding up that integral. This really is the code that you could use to integrate that function in closed form, and I can evaluate it on a grid, and I can do it for my 2 variance hypotheses. And here's what I get when I do that. The green variance hypothesis gives me this integrated mean squared prediction error surface, and the blue one gives me that one. And I want to minimize variance, so they recommend 2 different acquisitions. The blue one recommends taking x equals 0.3, and the green one recommends 0.35. So they're very close to one another. They kind of agree on the part of the input space where you would acquire more data. But the green one, importantly, says that you want a replicate. So even though you already have a good idea of what the variance is there, you want even more information about it because that will be more efficient statistically to reduce predictive uncertainty. So I think this result, well, I haven't shown you the result yet, but I've shown you the example, is the first one in the computer experiments literature which shows that there's a situation in which you would prefer a replicate in your design. And I don't think this has been studied previously because historically in the computer experiments literature, the noise was either low or non-existent. But when there is noise, you do want replication under certain circumstances. And in fact, we can describe those circumstances. It involves another mathematical formula that I'm not going to go through, except to say the following. When you believe the noise is bigger than something. So in other words, when you believe the noise is high, that's when you want to replicate. The next point will be a replicate when your belief about variance is big enough, bigger than something, and that something is a complicated formula. I could put that formula into a function and evaluate it for you so you can see it visually. The gray line here is the threshold at equality. So as long as your noise is everywhere bigger than the gray line, which it is for the green line, then you will want to replicate. And this is intuitive, right? Because intuition says when noise is high, that's when I get the most value from replication. And this tells you what high enough means, and also tells you at what input you want to obtain that replicate. All right, let me finish out this talk with a few illustrations. I don't think this will take more than 5 or 6 minutes, so we'll end on time. Here's a synthetic example that's a lot like the motorcycle data, but allows us to probe it over and over again so we can try this sequential design approach and learn the nonlinear response surface and the input-dependent variance, which is high here and low here, and then gets a little higher again at the end. So I got to bootstrap the whole process. I'll start with 10 training data locations, evenly spaced in the input space. I'm going to optimize IMSPE with a function that comes with our software package. Our IMSPE criteria has a look-ahead feature, which I did not talk to you about, but I can talk more offline if you want. And it comes back with an answer. This is the location that you want to add into the design, which is this number here. And you can see it's different than any of the other previous numbers, so it's not a replicate. of any of the locations that we've included in the design so far. I can augment the data with that new input and its output that's simulated from the function, and I can use the update function in our package to do that quickly. Now I'm going to repeat that over and over again before I make a plot for you. I'm going to gather a total of 500 samples in exactly this way that I showed you on the previous slide. 500 is more than you really need in this simple problem, but it's pretty fast to get all those. The Gaussian process computations are not expensive, and it allows us to view long-term behavior, which I'm going to show you on the next slide. So here is what we learned about the function. We learned it's noisier here than it is in other places. I've taken more points in the noisy region, so those are the open circles. The gray bars are helping you see true replicates. So it's a little hard to see that by just looking at the black dots, but if you want to know how many are replicated, that's the height of the gray bar. So I have the most replicates at this location here, and the second most at the edge of the input space. Yeah, so it's doing about what you would expect, more replicates and more dense sampling altogether where the noise is higher. More realistic examples. So here's the ocean oxygen example from before. Same R code as in the example we just did, but now I'm using the ocean oxygen simulator, and I'm being careful to evaluate to the same budget as we had done in the early experiment where we had 500 total evaluations. And as you can see on this slide, the allocation of that budget was much more interesting than 20 replicates at each, and the resulting response surface is far more nuanced as a result. Each of the numbers is a number of replicates, and you can see that the highest number of replicates, which I think is 8, is in the high noise region, in the yellow region. The second highest, 7 and 6, are at the boundaries between the high noise and the low noise region. Something to keep in mind about this is that the model doesn't always get it right. As it's learning, it might have the wrong idea about what the variance is. And the only way it learns about what's right is by taking more data and eventually determining that the noise is a little lower there than at first it might have believed. So you won't always see the highest number of replications in the highest noise region. What it's really looking for is these transitions between high and low noise. All right, we did a Monte Carlo experiment on this data. We repeated it over and over again with different random initializations. We compared homoscedastic Gaussian processes with static designs, the heteroscedastic Gaussian processes with static designs, the heteroscedastic Gaussian processes with sequential designs, and of course that last one was the best. It gave the most accurate predictions, lowest RMSE, and highest scores. And in fact, one of the interesting things we saw from this experiment is that fitting a heteroscedastic model is risky. If you don't have the right design to learn about how variance is changing in the input space, you can actually do worse than if you fit a simpler model. Maybe that isn't surprising, right? There's estimation risk involved in anything that's highly parameterized. And the heteroscedastic GP is highly parameterized because it has lots of latent variance variables. So if you don't have the right data to learn all those latent variance variables, then you don't predict particularly well. It's important to design the experiment in baby steps in order to get that right. All right, the last thing is this 8-dimensional problem that we skipped over very quickly. You'll recall that we did 1,000 unique inputs and 5,000 total with about degree 5 replication. We did a sequential experiment with almost the same number of unique, well, we didn't know what was going to be unique to start with. This we had control over. So we decided that we were only going to do 2,000 runs, not 5,000 runs. But instead of committing to a design in advance, we're going to build it up sequentially. So we did a much smaller campaign, 2/5 of the computational expense involved in the campaign. But what we got was predictions that were more accurate. So if you compare the out-of-sample scores of these two methods, the adaptive one is more accurate despite being based on a much smaller training data set. So that's what I came to talk to you about. Let me recap. When the mean and the variance are changing in the input space, it's still possible to get very accurate fits with Gaussian processes by coupling two of them together, one for the mean and one for the variance. And it could be advantageous. In fact, you could say it's almost required to have replication in the design so that it's both computationally and statistically more efficient. In fact, the more the variance is changing, the more replication you'll have. And that makes sense intuitively because you have a tough job of separating signal from noise. Everything that I showed you is available in our R package. This talk is reproducible. I'll share it with you if you want, but we have an even better thing, which is a vignette that comes with the package, which is like a bigger version of this talk with a lot more words written down that you can use to reproduce these examples. And the last thing I want to end with is a shameless plug for my book, which is an even bigger version of this talk and a lot of other topics involved in surrogate modeling. So it's a book on Gaussian processes, primarily for computer experiments. I talk about calibration and sequential design and uncertainty quantification and Bayesian optimization. There's even a chapter on heteroscedastic modeling and other advanced topics. And it's free. You can access it electronically on my webpage for free. I'll appreciate it if you buy a copy. It's expensive, but all the money that I get from it will be used to buy you a beer the next time I see you. All right, thanks very much again for the invitation and for your attention. And yeah, thanks.